town has a population of 5,300 people and grows 1.4% per year. What is the size after 1, 2, 5, and 10 years? For percentage growth, really what we're talking about is whatever grows above 100%, because 100% means it stays the same. So 100%, we're going to go add that on to their 1.4%. So it's the same thing as saying 101.4%. So in other words, what we're going to multiply by is the decimal number of this percentage. So it'll be 1.014. That's our multiplier. That's the growth rate. Because it's above 1, that means it's growing. If it were less than 1, then it would be decaying. It's actually getting smaller. So if we're talking about after a single year, that's the same thing as saying 5,300 people times 1.014, and that's going to grow to a larger quantity. And we can do that by plugging this into a calculator. So 5,300 times 1.014, and there we go. We get 5374. We're going to round down, of course, to the whole person. 5374 after 1 year. Okay, after 2 years, it's the same thing as saying 5,300 times 1.014, and then, which we just calculated, right? It'd be 5374, and then we're going to multiply this number by the 1.014 again, which is effectively the same thing as just saying this times by 1.014. This is our 50 or 5374, and that's being multiplied again by 1.014. And that's going to give us 2 years of growth, 5374 times by 1.014, and I get 5449. And then you can see the pattern continues for 5 years of growth. That's the same thing as taking this and timesing by this growth rate for this is the first year of growth. This will be for the second year of growth. This will be for the third year of growth, the fourth year of growth, and finally the fifth year of growth. So that's 1, 4. But we can use rules of exponents here to make it a little bit clearer what we're talking about. These are all just to the first power because they're all just multiplying by the number itself. So we can always put a power of 1 on any number. And we are multiplying like bases. So by rules of exponents, if you multiply like bases, you can add the exponents together. So in other words, the 1.014, the 5300 is not part of this. We're only combining these like bases of 1.014. And we're going to add the exponents. So it's going to be 1 plus 2 plus 3 plus 4 plus 5. So there's going to be 5 of them. And we can plug it into a calculator, and we will see we get 5,300 times 1.01014 to the power of 5. And it's 5681.5. So we'll round to the nearest person, 5682. So 5682. Of course, for 10 years, it's the same process again, except now we're going to have 10 of the 1.014s. So in other words, it's the same thing as saying 5300 times 1.014 to the power of 10 now. Instead of 5, we're talking about 10. This was to the power of 1. Then here we have to the power of 2, since it was 2 years, then 5 years, then 10 years. And that, I can just take this and change the power on this number here. We get 6091. That's the population of this town if it grows at this constant rate. Now, what model can be used to describe the simplistic situation? Well, we already see how it's growing here. We have 5,300 times 1.014. This one's going to be 5,300 times 1.01 squared because we have 2 of them. Of course, here we have 5,300 times 1.014 to the 5, and 5,300 times 1.014 to the 10. So if we're going to talk about for a generic year t, So I can talk about any year that I want. I can even talk about half years, things like that. And I'm using T for time. That's the designation there. The model for this is going to be 5,300 because that's our starting amount times 1.014 to the power of t. Since if t is 1, that's after 1 year, I get this first case of 5374. If t is 2, I get after 2 years 5449. Then if t is 5, I get this. If t is 10, I get this. I can, of course, do t equal to 1.5. In other words, what's halfway into that second year. You can do all sorts of things with this model since now I have no restrictions on t. That's the benefit of using the model. However, this is a very simple model. It doesn't consider any kind of changing rate of growth. It's only using kind of an average growth rate, and so it only applies to very simple ideas of what you're talking about. Okay, let's move on. According to the USGS in 2017, there was about 1.87 billion hectares of cropland on the Earth. What is this in scientific notation? Move really quick. Can you see that? 1.87 billion. Billion is going to be 1,000 is 3, million is 6 zeros, and billion is going to be 9 zeros. This is the same thing as 10 to the 9 hectares. 1.87 times 10 to the 9. So 1.887 billion is the English way of using scientific notation. That's the relationship there. But if each one of these hectare is 10,000 meters squared, what is this in meters squared? Well, this is the same thing as just saying 10 to the 4, right? We have 4 zeros there, so that's the same thing as saying 10 to the 4. So all we have to do really is just take 1.87 times 10 to the 9 hectares. We're going to multiply this by 10 to the 4 meters squared over 1 hectare. And the hectares cancel, and now we just have meters squared. So we get 1.87 times 10 to the 9 times 10 to the 4 meters squared. We are multiplying like bases here. 10 to the 9 times 10 to the 4. We can add the exponents since we're multiplying like bases. It's going to be 1.87 times 10 to the 13. 9 plus 4 is 13. And why is scientific notation used here? Because if I didn't use scientific notation, I'd have to write it as 187, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. Because I'd have to move the decimal point back 13 spaces, and that's what that would be. So that's going to be is 1, 2. It's a lot of zeros. It's very, very cumbersome to use this number versus the scientific notation number. A lot less writing there. So it's very important to use scientific notation for these large or very small numbers. Now, suppose the Earth is a sphere. It's not. The sphere is mostly water, and it spins, which means it's going to bulb out around the equator where it spins at. So it's not really a sphere, but we can approximate it with as a sphere. And the radius is going to be 6.371 times 10 to the 6 meters. If approximately 71% of the Earth's surface is water, what percentage is cropland? So first off, we need to figure out what percentage of the Earth's surface, or what surface area of the Earth is land. And then we can figure out what is the percentage of the land. This really should say what percentage of Earth's land is cropland. That the surface kind of means both land and water. But what I meant here with this question is what percentage of the land is used for cropland of the things that we can inhabit if we don't inhabit the water, right? Um, how much of that is used for food or any kind of crops? So if 71% is water, that means that 29% of the Earth's surface is actually land. So what is that as a number? Because we have the meters squared, the area, the surface area of cropland. So what's the surface area of land? Then we can divide those two numbers to get a percentage. Okay. The surface area formula is 4 pi r squared for a sphere. So the surface area of Earth is 4 pi times the radius, 6.371, times 10 to the 6 meters, and that is being squared. Now here we can see that we have a multiplication on the inside of a power. So we can actually distribute this power by rules of exponents. That's going to give us 4 pi times 6.371 squared times by 10 to the 6 squared. Of course, here we have a power to a power, so we're going to multiply the powers together. Again, a rule of exponents. 6 times 2 is 12, so this is the same thing as just 10 to the 12th. And we are having meters squared because also the unit gets squared, actually. That should be distributed onto the unit as well. Okay, I forgot the 1 here for 12. All right, so 4 pi and this 6.371 squared, we can put that into calculator. 4 and pi and Desmos makes the pi symbol. 6.371, and that is squared. We get 510.06. I'm just going to leave it as 510. There's only three decimal places in this 1.87 billion. Even though we have 4 here, it's going to be only 3 in the end, and it's just an approximation anyway. So that's why I'm only using 3 significant figures. Anyways, 510, we get 510 times 10 to the 12, because this part is still there. This is in meters squared. Of course, this is not in scientific notation. I can do that by just changing this 510 to be 5.10 times 10 to the 2 times 10 to the 12. And we have like bases, so we can add the exponents. 2 and 12 is 14. So 510 times 10 to the 14 meters squared. Now, to find the percentage of the Earth's land that is cropland, all we have to do is take the cropland, which again is this 1.87 times 10 to the 13, and divide it by the total surface area of Earth's land. So 1.87 times 10 to the 13 over 5.10 times 10 to the 14. And of course, this is in meters squared, and this is in meters squared, and the units cancel, which is what you expect for a percentage. Okay, so 10 to the 13 divided by 10 to the 14. Here we're dividing like bases. That's the same thing as subtracting the exponents. So 1.87 times, or divided by 5.10. This is going to be times 10 to the 13 minus 14 is negative 1. And you can see that I don't have that in the denominator. I could put it in the denominator as 1 over 10, right, by the rule of exponents. But let's see what 1.87 over 5.1 is. 1.87 divided by, we get 0.36 repeating. Times 10 to the negative 1, which is the same thing as 0.036. And I'm going to round to 3 significant figures here. In other words, we have 3.67% of the Earth's land is cropland, a very small percentage, and that's for the entirety of human, survival. Is That's how much land is being used to grow food and all the other crops we use. Even like coffee and things like that. So quite a small percentage for the entirety of Earth's population. Okay, let's move on. 1 kilogram is approximately 2.205 pounds. If a neutron, one of the 3 subatomic particles that make up an atom, if a neutron weighs around 1.675 times 10 to the 2, that did not correctly copy over, it should be negative 27 kilograms. How many neutrons are you effectively lifting when you lift a 30-pound weight? So there's a couple ways we can do this. Of course, we can do pounds to kilograms and then divide that out. Or we can do kilograms to pounds and then divide it out. Either way, you should get the same answer. Let's do pounds to kilograms and go from there. So we have 30 pounds is the same thing as 1 kilogram over 2.205 pounds. And you can see those units cancel. That's going to give us 30 divided by 2.205. And we get 13.61. I'll just do 13.61. Okay. And now we know that a single neutron is 1.675 times 10 to the negative 27. So all we have to do is figure out how many times can that weight of the neutron go into um, this mass of the weight that we're talking about here. In other words, we're going to divide it. So 13.67 divided by 1.675 times 10 to the negative 27 kilograms. This is kilograms of the weight and the kilograms of neutron. Of course, those cancel and just give us a number. The units, you can make it so that it's units of, or the number of neutrons, but that's not really what's important here. What's important here is the note that the units do cancel, and we're talking about a count, not a weight, of something, because that wouldn't make sense for the units. But we can see that we have times 10 to the negative 27 in the denominator. By rules of exponents, I know that should actually go into the numerator because the negative flips the position. So we're going to have 13.67 times 10 to the 27 over 1.675. So all you have to do is just figure out what is 13.67 divided by 1.675. 0.675, and we get 8.16, or just 8. Everything here is being estimated anyways. I do have four places, but this is a 30-pound weight, so that's probably only one makes sense there. We'll do 8 times 10 to the 27. And this, of course, is the count. This is the count of neutrons. So that's quite a large amount, but of course, neutrons are very, very, very small. Okay, if the side length of a square doubles, triples, is cut in half, by what factor does the area change? Well, we know that the area of a square is the same thing as x squared, where of course if we have a square, the side length is x. So what happens if we go from this to being, it's not the scale, which is, don't worry about the scale part. Where's 2x? Of course, all the sides are the same because I specified this shape as a square. So these are all 2x here. What happens to the area? Of course, here this changes. I should do area of x, and then this becomes area of 2x equals 2x, and this is being squared. Of course, we have a thing that's multiplying on the inside of a power. This is the same thing as 2 times x, and so 2 times x, this can be rewritten by distributing the power as 2 squared times x squared. But 2 squared is just 4, and x squared, we already know, is the area of the square. So let me do it like this, make it a little bit clearer. This portion is just this, which is just this. In other words, we get 4 times area of x. So in other words, area of 2x equals 4 times area of x. So the area of the original square, sorry, the area of the new square, the one that's extended by a factor of 2, is 4 times the area of the smaller square. And that should be kind of understandable. If we break up the thing here, right? Break it like this, and we get x, 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 right? This is the same thing as just one of these. Because if you sum up the side lengths, right, that's 2x. Well, the same process applies, right, for a triple. we have the area of 3x is going to equal 3 times x squared. That's going to be 3 squared times x squared, which is just 9 times x squared, which is, of course, is 9 times, what I have is the area of x. There's going to be 9 of those smaller blocks rather than just 4 like I showed here. And finally, if it's cut in half, well, same process applies. 1 half x equals 1 half x squared. Again, rules of exponents, that's what I'm using here. X squared, of course, I can make this a negative power if I wanted to. I don't have to. I'm going to 1 over 4 x squared, which of course is just the area of x. So we have 1/4. It's always double, or yeah, the squared power of whatever the multiplier is here. You can also write this as 4 to the negative 1 of the area of x. All the same thing that we're talking about. Now, what about this situation with a cube? So a cube, of course, three-dimensional, and we're talking about the area of x, or sorry, the x there. The volume is what we're talking about for a cube, for a three-dimensional object. Well, the volume is just x cubed, and double if we double the side length, then we're going to get vx, or I should do v2x equals 2x cubed, or 2 cubed x cubed, which is 8x cubed, which gives us 8 the volume of x. That's what, right? Well, once again, this x cubed is right there, which means it's just vx. So if we double the side length of a cube, we actually get 8 times the amount. And that can kind of make sense, right? If you have a cube like this, that's double the side length, then really you're cutting up all of these side lengths here into 4 spots. And you can see there's, let's see if I can draw this out. This is 1 cube here. 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 That's all 1 cube right there. This is 1 cube back here, 1 here, 1 here, and then there's 1 on the very back. That's 8 total that you can count. So that's where that 8 comes from. And the same process again applies to tripling. 3x cubed. We get 3 cubed. X cubed is now 27 times x cubed, which is the volume of x. There's going to be 27 cubes inside that bigger cube. And finally, if we half the side length, 1 half cubed times x cubed, we get 1/8 the volume of x, or again, 8 to the negative 1 power, the volume of x, using rules of exponents. So it's going to be 1/8 of the size, or 1/8 of the volume of the original cube. Okay, let's move on. Intensity of light can be modeled with this equation here. Let me just erase this a little bit. I equals k over d squared. D is the distance away from the light source, and k is just some constant. That constant really kind of depends on the situation you're talking about. But what happens to intensity if distance doubles? So in other words, we're saying what happens to the intensity, I'll do intensity 2, if k, if distance here is doubling. So instead of d, I have 2d that I plug in. And that's going to give us k over 2 squared d squared, which is the same thing as k over 4 d squared. So let me write it like this. I can break up the fraction if it helps like this. I can do like this: 1/4 times k over d squared. Right? When you're multiplying fractions together, you just go straight across top and bottom. So if I multiply this thing out here, I do in fact get back to this thing. So they are effectively the exact same thing. But now you can see that this portion here is just the original intensity that we were talking about. So we get 1/4 times I. So if we double the distance, the intensity becomes 1/4 of the amount, right? If you take a light source further away, it's not as bright, which makes sense. Okay, rewrite the equation with negative exponents. So again, the variable here is d. So I'll say I2, or I can write it as I1 k over d squared. It's the same thing as k times d to the negative 2. That's with negative exponents, right? If it's in the denominator, I can move it to the numerator with a negative exponent. And how does this relation contrast with a doubling of the side length of the square and its area? Well, this is the exact same thing as really talking about the cutting in half of the side length, right? When we did that, we had this one fourth uh, 1/4 the amount. Whereas here, when we took a double, let me highlight it here. When we took a double, we got 4 times the amount, and when we took a half, we got 1/4 the amount. So this what I'm showing here is the same, really effectively the same thing as this. This is 1/4, halving the side length of the square. The reason why I'm pointing this out here is because what I had here for the area, a equals x squared, and here I have I equals k over d squared. This is the variable of choice, and this is the variable of choice. Of course, this is just x squared, but this was k times d to the negative 2. The variable that we're talking about is x in the first one and d in the second one. X is positive, so when you increase x, it increases a. When d is increased, I is decreased. So if you do the same process, if we increase x squared, we increase a. That's what we saw. When we doubled x, we got 4 times the amount, and when we tripled x, we got 9 times the amount. If we decreased x, then we decreased a, right? If we decreased x, we decreased a. That's the same relationship. If you, instead of going up and up, you go down and down. Whereas the intensity of the equation, right? When I increased d, I doubled the distance, I actually decreased I. And vice versa. If I were to decrease d, I would increase I. So this is the situation here. In this first case, we have what's called a direct relationship. If you increase the side length, you increase the area. If you decrease the side length, you decrease the area. It's a direct one-to-one relation. Well, it's not one-to-one, but it's a direct relationship. Whereas the intensity of light is an inverse relationship. If I increase d, I decrease I. I increase the distance, I decrease the intensity. Or if I decrease the distance, I get this, the light source closer to what I'm talking about, then I increase the intensity of light. It's a inverse relation. And that's really all based on this power here, right? I have a power of 2, I have a power of negative 2. Okay, let's move on. Inflation is a devaluation of currency. So it's the same thing, same idea is that we need more money in the future to buy the same amount of goods today. So as in this example, if a food item, whatever food item might be, like chips or something like that, is $5 3 years ago, but today it is the exact same quality and the exact same quantity, but it's $7. That means the dollar has deflated, or sorry, inflated, and actually has become worth less. What is a 50% or $50,000 per year salary today, equivalent to 10 years from now with 2.5% inflation per year? Well, this is very similar to that growth that we talked about. $50,000 times this 2.5% inflation. That's the same thing as saying 100 plus 2.5% is 102.5. So we're going to take 100. Well, this is, as a decimal is 1.025. 1.025, and we're going to do that 10 times because we're talking about 10 years. Same thing is to the power of 10. Well, calculator can find that really quickly. Or I should say, sorry, it's not. I'm not increasing the amount. I'm decreasing the amount because it's actually making the quantity worth less. So I should be actually subtracting it here, not increasing it. So it's going to be 0.975, or I should say 97.5, and that becomes 0.975. Okay, so 50,000 times 75 to the power of 10. Let's see, 38,816. I'm just going to do just the whole numbers there. 38,816. So this is the amount that it's worth if everything were to stay the same. All the amounts of the dollar amounts of items and everything, if they all stay the same, but your dollar amount got inflated, it's effectively this amount today, if that makes sense. You can go the other way, whereas I could increase the amount, right? I could multiply it by 1.025. Let's just do that really quick, just to make sure we're on the same page here. To the power of 10. What this is saying is that $64,000 10 years from now is effectively the same amount as $50,000 today. So if you don't get a raise each year, but you make $50,000 each year, then that means you're actually making less and less each year. Effectively, what this is saying is that if you don't make a raise and um, you're making less money. That's the whole idea here that you're supposed to get. Now, what happens if you were to get a 2.5% raise each year to cover the inflation? What does that look like? Well, that's the same thing as saying $50,000 times by this raise, and it's 10 times, but you're also deflating the value of the dollar at that rate. What does that give you? If your answer is the same amount, well, we can check it with the calculator, right? We can go $50,000 times 0.975 power of 10 times by 1.025 to the power of 10. And you can see we actually have less money than we started with. 49,688. That's because to get back to the amount that you started with, you have to have a larger percentage raise. If I decrease by 10%, but then increase by 10%, then I actually have less money than I started with. So a 2.5% quote unquote raise would not even cover inflation. And in fact, this would not be considered a raise. This would be considered a cost of living adjustment. It's a different thing entirely. Now, what you could do is get like a 3% raise, or well, I should say again, quote unquote raise, be a cost of living adjustment. If we did that instead, then you see we actually do cover the inflation. Now, that doesn't mean we're actually making more money. That means we're just covering the loss of our dollar power um, over the 10 years. To get a raise, you'd have to have something significantly more than this. So something like 7%, or maybe 5% if it's a 2% 2% per year inflation rate, which is typically what they try to shoot for, the government.